Hello, my name is Stefan Bühler and welcome to our poster presentation about our paper Defensive Perception, Estimation and Monitoring of Neural Network Performance under Deployment. In autonomous driving, it is crucial to know if an autonomous vehicle left the operational design domain and in general anticipate uncertainty of the perception system. In this paper, we propose to address this by encapsulating the model within an uncertainty estimation envelope that is based on the Monte Carlo dropout approach. This approach does not require modification of the deployed neural network and guarantees expected model performance. The defensive perception envelope has the capability to estimate the neural network's performance and is extended by novel methods to reduce computational effort. Here you can see the system flow overview. Since the perception stack is trained for only one source domain or specific source domains, the defensive perception envelope informs the system if an unknown domain was entered and as uncertainty rises. On the top here you can see our metrics that we used to estimate that uncertainty, and as already mentioned, we used the Monte Carlo dropout approach, which means we have multiple forward passes with the same input data and the same model, but we insert a dropout layer and that allows us to have the possibility to have different predictions for the same input data. We then try to measure the difference of these predictions with the pseudo-cross entropy metric that is written down here. The advantages of this metric are it is independent from the number of forward passes, it depicts the entropy emerging from multiple forward passes, and it smoothes the uncertainty for small deviations while upscaling larger ones. Our first experiment was with the MNIST dataset. The MNIST dataset, I'm sure you all know it, is the dataset with handwritten numbers where you have to predict the number from the image. The model was trained on the standard dataset, so the numbers were not rotated, but for the test set, the numbers were rotated anticlockwise up to 90 degrees in 10-degree steps. Then the uncertainty was calculated with our new uncertainty metric using 20 forward passes, so 20 predictions per number, and with a dropout rate of 0.4. Also, the error was calculated to compare our uncertainty metric, and we also looked at the maximal number from the one-hot vector. If we now look into this graph, we can see that the maximal one-hot number nearly drops, while our uncertainty value increases down here, up to about 0.4. Yeah, if you want to do this experiment yourself, you can follow this QR code here and you will find a notebook where you can find the code for that. Now coming to an autonomous driving problem, we have switched over to a dataset that uses semantic segmentation on street images. And yeah, the first experiment we did was to train a model only on day images, so on the day domain, and then switch the model over to the night domain. So use the same model that was trained only on day images on night images. And then we want to see if we can use our approach to see the uncertainty within the model. In the first image, you can see the input images. You can see two input images. In the second image, you can see one model prediction. Of course, there are more predictions for the same image. That's how the Monte Carlo dropout works. And in the last image, you can see for every pixel calculated the metric up here. And yeah, the more red the pixel is, the higher the uncertainty is within that area. Below here you can see a plot showing the correlation between the error and the uncertainty of each image. The error was of course calculated with the label, corresponding label of the image, and the uncertainty calculated as explained. Here you can see the corresponding errors and uncertainties for the day model trained on the day domain, on the day images and on the night images of the test set. Here you can see it again for the day images and compared to the dawn images of the test set. And on the right here, we did another experiment by training a model only on clear data, so dry streets, and then using that same model with rainy data and with snowy data. Yes, there is one problem this whole approach has, which you probably already noticed, and that is that it's the computational effort for it. We use multiple forward passes on one image, and yeah, that would probably not be possible to deploy in an autonomous driving system because of the limited resources. To avoid this problem, we used now sequential data to calculate our uncertainty. For that, we did different experiments at different frame rates to see how changes in images affect this approach. As you can see, there is more uncertainty here or maybe to explain the plot first, the dotted line shows our baseline. So our normal approach, just the Monte Carlo approach on one image, so it's the same because it's not dependent on the frame rate. We just use the same image, and the solid lines are using the sequential images. We call this rolling Monte Carlo dropout because we use one image after each other. So we only have to do one prediction per image. Yes. And as you can see, for 30 frames per second, the uncertainty is lower as for 5 frames per second. And that is because there is uncertainty introduced because the input image now changes a little bit. But if the frame rate is low enough, and so the changes from one image to another is low enough, we can still use this approach because the newly introduced uncertainty that comes from input image differences, is not high enough, or can be not high enough if the frame rate is high enough, that we can still detect if an image is out of domain or not. So for example, if we take these images down here, changing one frame from another, things change on the left or on the right. But if we have an image like this, it would still detect the higher uncertainty on the lower one. We just have to take into account the uncertainty introduced due to input image differences. Another problem is that I now want to address is that we introduce a dropout layer in the model, and that of course, and now of course we have to see if we need another pure inference pass. What that is, that means is an inference pass that is not using any dropout. But we did some experiments, and within a certain range of dropout, the model can still be safely used. Only if we get a really high dropout rate, like for example the 0.9 dropout, so dropping 90%, is then of course the error increases a lot. But if we stay within a mid-range, we can still profit if we go over 0.2 from the Monte Carlo dropout, and we still have a low enough newly introduced error due to dropping connections. In conclusion, we introduced a new method for performance estimation of neural networks under deployment. What the method can do is to prevent an issue of unnoticed catastrophic deployment due to a domain shift. It can also detect the uncertainty within a model and provide warning notifications or save state triggers if high enough uncertainty was detected. And also, due to the introduced rolling Monte Carlo dropout, we were able to reduce the compute expenses that come from normally come from Monte Carlo dropout by doing the multiple predictions on the same image. That was my poster presentation. Thank you a lot for listening, and goodbye.